Hello everyone. In this video, I will talk about compressive strength test performed on hardened concrete specimen. This test was standardized by ASTM C39. It's the most common test by far performed on concrete specimens, even more common than slump test. The standard specimen size is 6 inch in diameter and 12 inch in height, although other sizes with a height to diameter ratio of 2 can also be used. We require the height to diameter ratio to be 2 because we want to eliminate the end effect due to the friction between the loading heights and the specimen. We want to produce a zone of uniaxial compression within the specimen. If the height to diameter ratio is less than 2, then a correction factor should be applied to the results. You can check about the correction factor from ASTM C39. The compressive strength of normal weight concrete measured by using this test is often between 20 to 40 MPa. 7-day strength, which means the compressive strength measured after 7 days of curing, is approximately 60% to 70% of the strength after 28 days of curing. And the strength after 28 days of curing is approximately 80% to 90% of the ultimate strength. So let's talk about the testing procedure. First, the specimens are prepared in 3 equal layers, and between each layer is routed 25 times. The specimens are then kept in mold for the first day and then removed from the mold and cured at approximately 23 degrees Celsius with the relative humidity of about 90%, 95% or higher until the time of testing. Before testing, the specimens can be kept at the 2 bases to ensure parallel surfaces. This step is optional. The specimens are then tested by applying actual compressive load with a loading rate of about 0.25 plus or minus 0.05 MPa per second until failure. Finally, the compressive strength of the specimen is determined by dividing the maximum load by the average cross-sectional area. There are 3 main failure modes. The first type is reasonably well-formed cones on both ends, which means the specimen fails in shear. The second type, well-formed cone on one end and vertical cracks running through the other end, so no cone on the other end, so which means the specimen fails in a combination of shear and splitting. So the third type is columnar vertical cracking through both ends, no well-formed cones, which means the specimen fails in splitting. On the YouTube video I provided to you, it talked about other failure modes. So in your lab report, you need to discuss the failure modes of your sample. Remember that the stress strain curve of concrete in compression is nonlinear. So how to calculate the modulus of elasticity, basically how to find the slope of this nonlinear curve. So in the first class, I talked about how to calculate the modulus of elasticity when the material displays nonlinear behavior. So we used initial tangent modulus, secant modulus, and the chord modulus. So the initial tangent modulus is the slope of the tangent drawn at the origin of the stress strain curve, and the tangent modulus is the slope of the tangent drawn at an arbitrary point on the stress strain curve, and the secant modulus is the slope of the chord connecting the origin and an arbitrary point on the stress strain curve, and the chord modulus is the slope of the chord connecting 2 points on the stress strain curve. So to calculate modulus of elasticity of concrete, we often use chord modulus. So this process is standardized by ASTM C469. And basically, we need to find the 2 points on this nonlinear stress strain curve. The first point, epsilon 1, sigma 1, is found by first finding epsilon 1. Epsilon 1 should be approximately equal to 0.00005. And the sigma 1 is the stress corresponds to this strain level. And the second point is located by finding sigma 2. Sigma 2 is the design stress, which is 40% of the ultimate stress. Remember that ultimate stress is the peak load on this curve, and then you can calculate the design stress, and the strain epsilon 2 is the strain corresponds to this stress level. Okay, so after you located these 2 points, then you can calculate the chord modulus E, which is equal to sigma 2 minus sigma 1 over epsilon 2 minus epsilon 1. The normal weight concrete often has a modulus of elasticity between 14 to 40 G-pa, and the Poisson ratio of concrete varies between 0.11 to 0.21, and we often use a value somewhere between 0.15 to 0.2. Remember, in the previous class, I provided an empirical relationship between the elastic modulus and the compressive strength of concrete. So basically this formula, and in that class, I provided the formula in terms of MPa. So this is the same formula but written in PSI. Actually, there is a more general formula, which is this one. It shows that the elastic modulus equal to 33 times W to the power of 1.5 times the square root of Fc. So Fc is the compressive strength, EC is the elastic modulus, and W is the unit weight of concrete. It can be somewhere between 90 pound-force cubic foot to 155 pound-force cubic foot. If W is approximately equal to 145 pound-force cubic foot, then you can directly use this formula. So in your lab report, you measured the compressive strength from the experiments, and then you calculated the elastic modulus. So you can check if the elastic modulus predicted by using this empirical formula can actually match your results. So finally, let's talk about the relationship between compressive strength, degree of hydration, and water to cement ratio. So from this figure, we can see that as water to cement ratio increases, the compressive strength decreases. And the compressive strength also depends on the curing time. So from this figure, you can see the compressive strength actually increases with longer curing time. So this is because curing allows continued hydration and consequently continued gain in concrete strength. In fact, once curing stops, the concrete will dry out and the strength gain will stop. So from this figure, you can see if the concrete is not cured and is allowed to dry in air, it will gain only about one half of the strength of continuously cured concrete. If the concrete is cured for only 3 days, it will reach about 60% of the strength of continuously cured concrete. And if it's cured for 7 days, it will reach about 80% of the strength of continuously cured concrete. So there is actually an equation to relate compressive strength, degree of hydration, and water to cement ratio. It's called Powers equation. It shows that the compressive strength equal to 100 times 0.68 alpha over water to cement ratio plus 0.32 alpha to the power of 3. Alpha is the degree of hydration. So in your lab report, you have measured the measured value of compressive strength. You also know the water to cement ratio. Then you can calculate degree of hydration and then discuss the relationship of compressive strength, degree of hydration, and water to cement ratio.